Hello, today we study numerical integration. Actually, in Calculus 1, when we start definite integrals, we learn how to approximate a definite integrals using Riemann sums. And that's how we can, define definite integrals, right? So we go from a function and you want to find the area of the region enclosed by the graph of some function, on some interval a and b, and you define the area is equal to definite integral from a to b f of x dx. And right now we learn a lot of integration techniques, but the problem is in real life there are a lot of functions that cannot be integrated. That means it's extremely difficult to find antiderivative of such functions, and you still need to find the area, or you still need to evaluate definite integrals of such functions. Look at this. So here are some examples. You see, it is very simple, right? So you know how to integrate the function 1 minus x squared, but you go to 1 minus x cubed, there's no way. You know how to integrate the function x square root of 1 minus x or x minus 1, but if you just change a little bit in here, there's no way to find antiderivative. Or you can find psi of x, but what is psi of x squared? You can find antiderivative of e to the x, but what is antiderivative of e to the x squared? Or cosine x divided by x. Such functions are a lot. There are a lot of such functions, So again, if you want to evaluate definite integrals of those functions, so you need to use numerical method. Okay. Riemann sum, of course, that is general, and today we will consider different kinds of Riemann sums, right? Look at this. Let me draw an arbitrary. You have y in here, x in here, and 0 in here, and suppose that your function look like this. Okay, so this is a, this is b. You want to find the area of this region. Okay, in Calculus 1 we use Riemann sum, but we use triangles, right? So you use left triangle or right triangle, right? For example, if you want to use left endpoints, so you have this. You remember that? So I need to divide, I need to divide the interval AB into subintervals, right? Sometimes you may use, subintervals of the same width. It would be easier for computation. Let's say, the length of each subinterval is delta x. And so delta x is equal to b minus a over n, right? That is the length, because you have n intervals. So if we remember the Riemann sum in that case, that is just, sum I from 1 to n f of xi star times delta x, where xi star is, an arbitrary point. It depends on you, but you might divide from xi to xi plus 1 or whatever, right? But in this case, if you determine I from 1 to n, so I would choose, xi from xi minus 1 to xi, because that's how you can run from x0 to xn. Okay, so you from that point you just choose arbitrary point, right? And it depends on if xi is end right endpoint or left endpoint, whatever you want, right? So you might have the Riemann sum, or you may choose, you know, endpoint in between each interval. Does that make sense? All right, that is about, you know, how we can use rectangles, right, to approximate our region. And now you have another method, you know, because you can see if you compare, right? So if you use rectangular, so you have, you know, very big arrow in here. Is that correct? Big arrow. So if you want to approximate not by rectangular and you want to use trapezoid, for example. So that is your interval, let's say this, and you connect these two guys, two vertices, and you have some trapezoid in here, right? And suppose that is xi plus 1, and then this point is f of xi, this guy is f of xi plus 1, and you can find the area of this trapezoid. Is that correct? And you can see the arrow in this situation is smaller, right? So, you know, that is the problem of numerical computation. If you want to get a smaller arrow in each step, so your computation would be faster. Is that right? So if I use trapezoid, I can write another Riemann sum. Okay, so the area of trapezoid, let me write here so you can see, you know, the picture all together. Trapezoid, the area is equal to 1/2. The height in this case is just equal to, you know, the distance between xi and xi plus 1, right? The height I write here, you know, delta xi, or just delta x, because if you choose, you know, interval of the same width, so you have delta x only, times fxi plus fxi plus 1. Why? Because, you know, what is fxi plus fxi plus 1? Fxi is this side. Fxi plus 1 is this, and the height is this. So, you know, you just take sum of fxi plus fxi plus 1 and then divide by 2, multiply with the height. You have the area of the trapezoid. Okay, now you run, right? You let I run from where? From 0 to n minus 1, or from 1 to n, whatever you want, right? But, you know, each time I can approximate the area of small piece by the area of trapezoid, and then I sum them up. I get a Riemann sum. Okay, so I can write the Riemann sum in here. That is just equal sum. Let's say I from 1 to n, right? In here I have 1 over 2. If I run I from 1 to n, so I need to start from I to xi minus 1, okay, plus f of xi in here times delta x. You see that? Because, you know, if I equal to 1, so I have x0, which is a, and when I equal to n, so I have xn, which is b. Okay, then, now when you sum them off, you get the following. I can take 1/2 out. Of course, delta x is also common, so I can take that out. And what is delta x? That is b minus a over n, right? We just calculate this right here. And inside, I will have f of x0 plus f of x1. That is from the first term, plus f of x1 plus f of x2, and so on, plus f of xn minus 1 plus f of xn. So each time when you start from x1, so you have 2 times x1 plus x1, and then you have x2 plus x2 right here, and so on. Overall, I have 1 or b minus a over 2n f of x0 plus 2 times f of x1 plus 2 times f of x2 and so on, plus 2 times of f of xn minus 1 plus f of xn, right? And this is the Riemann sum if we use trapezoids. And as we just discussed in this picture, right, if you use trapezoid, so the computation would be faster, right? And the error would be less on each step. So, this is one of the methods they may use. Okay, so let's consider the following example. You had function sub x dx, right? And let's say sub x squared, because sub x is easy. Sub x squared dx. You want to evaluate now definite integral from 0 to pi sub x squared, and they ask you to use trapezoids to approximate this integral. Okay, let's for n equal to, let's say 4. Okay, you pick n equal to 4, right? And we need to use this formula. That's it. Just be careful, right? So I can write, actually in this case I have integral from 0 to pi psi of x squared dx is approximately equal to b minus a is pi minus 0 over 2n, 2 times 4. So I write f of x0 plus 2 times f of x1 plus 2 times f of x2, okay, plus 2 times of f x3, and then f of x4. Right now I don't see, I don't write any about x0, x1, x2, x3, and x4. Now we can find them right here. So your interval from 0 to pi, right? You divide this into 4 subintervals. So you have pi over 2 in here, pi over 4 in here, and 3 pi over 4. You see? That is your x0, that is your x1, that is your x2, that is x3, and this is your x4. So now you just plug those values into this formula. So you have f of x0 means f of 0, which is psi of 0, equal to 0. You have f of x1 is psi of pi over 4 square. You have f of x2 equal to psi of pi over 2 square, and you can write f x3 is psi of pi over 4, 3 pi over 4 square, and f of x4 is psi of pi square, right? And then you plug all values into this formula and you're done. You use calculator to find that. And that's how you can approximate integral from 0 to pi psi of x squared dx. Okay? Let's do this, for psi of x dx, 0 to 2 pi. Okay? Again, use trapezoid rule for n equal to 4. And let's compare with what we have. If we can evaluate this, that is negative cosine of x, evaluated from 0 to pi. So that is negative cosine of pi minus cosine of 0. So you have negative 1 minus 1, that is 2. And of course, in this situation, everything is good. If you want to use n equal to 4, again, you have 0 pi, and then you have pi over 2, you have pi over 4, then you have 3 pi over 4, right? And we use almost the same thing, but you know, instead of x squared, we have just x. Is that correct? So I need to find f of 0 is 0, f of pi over 4 is sine of pi over 4, which is square root of 2 over 2. F of pi over 2 is sine of pi over 2 is 1. F of 3 pi over 4 sine of 3 pi over 4, right? That is again square root of 2 over 2. And f of pi is sine of pi, which is 0. So again, you plug all this value into the formula, you get approximately, you know, integral from 0 to pi sine x dx is b over a is pi over 2n, which is a, and then you have square root of 2 over 2 plus 1 plus square root of 2 over 2, and that is, you know, pi over 8 square root of 2 plus 1. So that's how we can use, you know, trapezoid for such integral. All right. Another problem when you use numerical integration is which method is faster, and you need to care about the conversions. Okay, you need to care about the, you know, the speed of computation and the conversions. So what does mean conversions, right? You know, when we increase the number of subintervals in here, is if you consider the limit, right, of the right hand side part, when n approaches infinity, you get that. So how fast you approach to the limit, that is about the divergence, the speed of divergence. Does that make sense? Now look at this picture, and we look at this from the point of view of approximation theory. So let me zoom the picture out, right? Let's say, yeah, we have interval xi and xi plus 1, xi plus 1. In this picture, we approximate using rectangulars, right? So for rectangular, you only need 1 point. You see this? You only need 1 point. Maybe left end point, maybe right end point, or maybe just some point in here. So that is the midpoint. Does that make sense? But you know, for the area of this, we only need 1 point, because if you have xi star in here, so you have f of xi star in here. And if you pay attention, the Riemann sum looks like f of xi star times delta x. So we need only 1 point on each subinterval. And we just talked about trapezoids, and we use trapezoids to approximate. And in the trapezoid formulas, we need, you know, on each interval, we need 2 points. You see this? And you know, that is what? That is f of 1/2 f of xi plus f of xi plus 1 times delta x. So basically, in this picture, we use a constant function to approximate. In here, we use a linear function to approximate. You know, what does it mean to approximate the area, right? So I may talk about, I approximate the curve. I approximate the curve on that interval, on the interval xy, xi minus 1, by a constant. You see this? By a constant by here. Because what that is constant. This is a constant, is that right? So I might think, yeah, okay, I use, you know, just a constant. But in this case, I use linear function. Because, you know, each time, you know, I approximate the curve using a linear function in here. It's a straight line, is that correct? So, you know, it is something like, if you remember the problem, how to find arc length, we approximate the curve, right? We divide the curve into small pieces. Remember that? And then we approximate the curve using you know, linear function in here, and we just calculate the length of each piece in here, right, of each interval, and then we sum them up, we get the final answer, right? We sum them up, and then we take the limit, and then we get this integral 1 plus f prime squared dx. That is about the arc length. So that's almost the same thing. All right, so you go from constant, that means, you know, polynomial of degree 0, polynomial of degree 0, to polynomial of degrees 1, right? So you might think about, you know, if you increase the degree of your polynomials, then your computation may be better, your approximation may be better. Is that correct? So that's why people try to do that, and actually they developed a theory how to use quadratic functions to approximate on each subintervals in here. So if you want to find quadratic, right, that means you need to use, you know, polynomials. Let's draw another one in here. So you have x, y, okay, again you have your function like this. So if you want to use quadratic polynomials, means, you know, px equal to ax squared plus bx plus c, you need at least 3 points. Is that correct? You need at least 3 points. So, you know, that means if they give you 2 points in here, and then you have to choose another point in here, right? And you need to find the parabola, the graph of that, you know, of which pass through these 3 points. Okay, so, you know, I don't know, right? But I can draw something like this, you know, that is my parabola. And, you know, that's how I can approximate the curve of the function on this interval using parabola. You see this? And there is a hope that, you know, using polynomials of higher degree, you get a better approximation. That is the hope. Okay? So you see, that is some kind of, I just want to explain the evolution, right, of the approximation theory. So that's what we learned from Calculus 1. We use constant functions. On each interval, you pick some point, you use the left or right or the midpoint, and you write the Riemann sum like this. So basically, you use constant functions to approximate your definite integrals. We just did using linear functions, right? So we use trapezoids, right? And now if we move to quadratic functions, so we use quadratic polynomials to approximate your function on each interval. Okay, and let's talk about this. So for this situation, we have so-called the Simpson's rule. Okay, we have Simpson's rule, and it says if you have polynomial px equal to ax squared plus bx plus c, then the integral from a to b px dx is nothing but, you know, b minus a over 6. In here, pa plus 4p a plus b over 2 plus pb. So what does it mean? That means you have, you know, quadratic polynomial, and you evaluate the definite integral from a to b, right? So let's say, I don't know about, you know, a capital, maybe that is bigger than 0 or less than 0, but suppose that is bigger than 0, right? And you evaluate from a to b, and, you know, the definite integral, let's say, yeah, that is some kind of, you know, area of this. Is that correct? So you choose the midpoint. You see, a plus b over 2. That is the midpoint of ab, right? So that is the midpoint. A plus b over 2. And then you evaluate the function value in here, the function value in here, and the function value in here. That is your PA. That is your PB, that is PA plus B over 2. And it turns out that the definite integral can be exactly computed using just 3 points, PA plus B, and PP. Means, 2 endpoints and the midpoint. That's it. It can be proved easily. You can see the proof in the textbook. So it says, yes, it is pretty nice. And then you can use this for each interval in here. So you might think, yeah, you choose xi at xi plus 1 and you choose the midpoint here, right? So if you want, you can find, you approximate, the function by some parabola. And then you can find the exact value, the exact area of each one in here, of the area enclosed by the parabola, right, on this interval. And you use that area to approximate the area of the small piece. Does this make sense? So if you use this on each interval and then you sum them up, right, you get a Riemann sum. So that is about the Simpson's rule on the whole interval. Okay, so I can write this in the following form. We suppose that the function f is continuous. So means the function is good on A and B. Okay, and let n be an even integer. The region of this condition is also clear because otherwise you cannot use 3 points on each subinterval. You see that later. Then the Simpson rules for approximating definite integral from A to B of fx is, you just copy this formula, but for n points, for n subintervals. So you have integral from A to B f of x dx is approximately equal to b minus a over, here we have 6, right, because 6 is 2 times 3 times n, and in this case 2. Is that correct? You have 2 endpoints. So here should be 3n. In here you have f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 and so on, plus 2 f of xn minus 1 minus 2 plus 4 f of xn minus 1 plus f of xn. And of course, when n approaches infinity, so you get exact value. Okay, so let's consider an example. Let's choose the one integral from 0 to pi psi of x dx. Then we have, let's pick n equal to 4 again. We use the Simpson. So I have integral from 0 to pi psi of x dx is approximately equal to pi minus 0 divided by 3 times 4. In here I have f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 and then plus f of x4. So f of x0 is what? Again, right, we have 0, pi over 2, pi over 4, and here 3 pi over 4. This is f of, I can write psi of 0 plus 4 psi of pi over 4 plus 2 psi of pi over 2 plus 4 psi of pi over 3 pi over 4 plus psi of pi. And then here you have pi over 12. So you just calculate this number and you get, the approximation. Let's find it out. So you have pi over 12. This is 0. So this is 4 square root of 2 over 2 plus 2 plus 4 square root of 2 over 2 plus 0, which is pi over 12. Here I have 2, 2. So basically that should be 4 square root of 2 plus 2, right? And that is, you can write pi over 6, 2 square root of 2 plus 1. Yeah, that's it. Of course, we still have some problems in the textbook, and even we can evaluate the errors in the trapezoid rule and the Simpson rules. But again, right, in order to finish this video, let's talk about error analysis. And for computation, I think this is the most important part, right? Because you need to decide which method is good, is better, and in which situation. So here we learn two rules: trapezoidal rule and Simpson rule. If f is a function, is continuous function, and the second derivative of f is continuous on AB, then the error E in approximating the integral AB fx by the trapezoidal rule is determined by this inequality. So the error is less than or equal to b minus a cubed divided by 12 n squared, maximum of the third derivative of the function on that interval on AB. And if f has a continuous fourth derivative, right, means the function is differentiable, but in the fourth term, right, there exists the fourth derivative, and that derivative is continuous, then the error in the approximating that definite integral is determined by this formula. It says, if you have, if the function f satisfies one of those properties for trapezoid rule or Simpson rules, you can make the error smaller as you want, because in this formula the second derivative is continuous, right? So this value would be about it. It's just a constant. So the error depends on the number n in here. Is that correct? So when you increase n, right, 1 over n squared is small and approach to 0. So that's why you can make the error smaller as much as you want. Is that correct? And it's almost the same thing for this situation. And if you compare two numbers in here you have 1 over n squared, right? And here you have 1 over n to the fourth. So you might think about this: 1 over n squared and 1 over n to the fourth. Which one approaches 0 faster? Of course, this one. When you increase n, right, 1 over n to the fourth decrease to 0 faster than 1 over n squared. So that may give you some feeling that if the function f is pretty good, means in this case has a continuous fourth derivative, then the Simpson rule works better than the trapezoid rule. Is that correct? Because the error in this case, you can make this smaller, and then that approach 0 faster than the previous one, than this one. Okay, but it really depends on the function. Does that make sense? So that is one side of this statement. Another side of this statement is, like previous example, they give you the number n, they give you the number of subintervals, and then they ask you to use one of those rules to approximate your definite integrals. But in reality, sometimes they don't give you n, right? And sometimes they give you the error. they require you to compute to approximate definite integrals with some error. So you need to determine the number n. And in that situation, these formulas help you to determine the n. For example, if I say, yeah, I want the error like, very small, 0.0001, whatever, right? So you need to compare this number with what? With the right-hand side part of this inequality. If you want to use trapezoid rule, or if you want to use, Simpson rule, and your function is good, you need to compare that number with the right-hand side part of the inequality. And you use that, you find a good enough number n. Because if they just ask you that, ask you to compute with that error, you don't need to make that better. Does that make sense? So let's consider the following example, and then we finish today's video. We have integral from 0 to 1, square root of 1 plus x squared dx. They ask us to determine the value n such that trapezoid rule will approximate the value of this definite integral with an error that is less than or equal 0.01. Okay, so that means we need to compare 0.01 with this part. Okay, let me write that. I need to compare. I will put, that part is b minus a cubed over 12 n squared. Here maximum second derivative of x less than or equal to 0.1. I think I did something wrong here. Here should be second derivative, not the third derivative. Because the second derivative, we have continuous second derivative, right? Then this number is is a constant and a finite number. Sorry for that. So I have this, and then I need to find second derivative of the function, right? The function is f of x equal to 1 plus x squared, and then you have derivative is x over, or let's use the power rule. So I write x times 1 plus x squared, and then 2.5. If I use again product rule to find derivative of this, I will get 1 plus x squared to negative 1.5 plus x times negative 1.5, 1 plus x squared to negative 3.5 times 2x. And then let's simplify this. And you get 1 plus x squared negative 1.5, 2 with negative 1.5, that will be cancelled out. Then I still have negative in here, x squared times 1 plus x squared negative 3.5. And if you take 1 plus x squared negative 3.5 out, right, you factor that out, then you have 1 plus x squared minus x squared. I think we did this several times in the past, and this is just 1, right? So I have 1 plus x squared and then negative 3.5. So that is my second derivative, and you need to find maximum of this function, right? So in this case, maximum of the second derivative x on the interval, our interval is 0, 1, right? Let's say on 0, 1 is, okay, let's write this, just 1 over 1 plus x squared and then 2, 3.5. So you can see the maximum would be 1 when x equal to 0. Is that correct? Okay, so I have maximum is 1. Then from the formula of the arrow, from this one, I have, let me write in here, okay, b minus a is just 1 divided by 12n squared times 1 less than or equal 0.01. And solving this, we can find the number, the smallest number n, that we need. So from here I get 12n squared greater than 1 divided by 0.001, which is 100, and n squared greater than or equal to 100 divided by 12, or n greater than square root of 100 divided by 12, which is approximately equal to 289. So that means, in order to guarantee the error which is less than or equal to 0.01, you just need to choose some n which is greater than or equal to 3.89. That means you only need to choose n equal to 3. That is enough. You see, you don't need to choose n equal to 4 because, when you increase n, you increase your computation. Does that make sense? So you just need to choose n equal to 3. And then once you have number n, you go back to the trapezoid rule. You just apply, trapezoid rule. Rule for n equal to 3, and you will get your approximation. Does that make sense? That's how all this works. But again, right? Of course, this is very, very important because, everything in this, right, you see on the screen has been done theoretically. As without this, of course, you can see we cannot choose a good n. Is that correct? And without this, we don't know how our computation, how good our computation is. And you cannot see the speed of convergence, because when you want to approximate and then you want to get the exact value of your definite intervals, you need to consider the limit. That means you need to consider the divergence or the speed of the divergence. Does that make sense? So I hope that you understand everything in this video and the main idea of numerical integration. And let's go back to this before we finish, right? And this is the main thing. So we approximate by constant functions, we approximate by linear functions, and we approximate by quadratic functions on each interval. And for each one, of course, you need to consider divergence. Okay? And the last example just shows you about that. All right. Thank you.